Hi guys, okay, this is my video number 5, my notes lecture number 5. Alright, in this video I'll talk on the solution of random integral equation. Alright, this is some notes that we need to know before we go to the detail of this the procedure of solving the random integral equation. Alright, so we call that the homogeneous random integral equation, the homogeneous without f0 here, okay, and then we still have the unknown inside the integral as well as outside the integral. And for non-homogeneous random integral equation, so we have this function in front of the integration. Okay, so the if u is 0, if u is 0, so this is a trivial solution that gives you this trivial solution to the equation, and the value lambda here for the non-trivial solution, which means for that give u non-zero, that will be known as eigenvalues of that equation, yeah, or eigenvalue of the kernel. So if there is typing error, there should be phi. If we let phi be continuous and phi different than 0, so in the interval 0 AB, then we have those phi x equal to lambda naught integration kxt phi t dt. Then this phi is known as eigenfunction, because this will act as a solution to our equation number 1 here. Okay, so known as the eigenfunction corresponding to the eigenvalue lambda naught. Now we note the following. Yes, so the number lambda, if lambda is 0, yeah, then lambda 0 is not the eigenvalue, because when lambda is 0, so definitely it will give us the trivial solution to our equation. So this is not the eigenvalue. So if the kernel K is continuous in the rectangle X between AB and T between AB and the number AB are finite, then to every eigenvalue lambda, there exists a finite number of linear independent eigenfunction. So the number of such function is known as the index of the eigenvalue. So we have those words there, index of the eigenvalue. So different eigenvalues have different indices, and if phi is an eigenfunction of the integral equation 1, means the homogeneous random integral equation corresponding to lambda naught, then for any arbitrary constant c, we have c phi is also the eigenfunction of the equation of the homogeneous random integral equation. And note number 4 here, homogeneous random integral equation may generally have no eigenvalues and no eigenfunction, or it may not have any real eigenvalues and eigenfunction. Alright, so that's a general notes that we need to know, especially on the eigenvalue and eigenfunction. Now we look at the detail of the solution of the integral equation. Now first we consider the homogeneous integral equation with separable kernel. Yeah, separable kernel. So what does separable kernel means? For the homogeneous integral equation, homogeneous random integral equation, which is of this form, lambda a to b xt ut dt. Okay, we call the kernel K. So this is named as a kernel, which is known. Okay, we say this kernel as a separable if we can write K in terms of summation of function of x alone and function of of t alone. So that's we call it as a separable kernel. So if given a kernel, and it can be written as that, so we call that as a separable kernel. So if you substitute this separable kernel into the Freedom integral equation, homogeneous Freedom integral equation, so what we have, ux is equal to, we have lambda integrate a to b sum in to I1 to n. So we have uix vit ut dt. Now, since the integration with respect to t, we can take out the function of x outside the integral. So that will give us and change the order of summation and integration. So we have lambda summation I1 to n, and then take out function of x, uix, then we integrate a to b vit ut dt. So what left now is we just need to solve or to integrate the function that involve t. Now, if we define this as ci, say, so we can write this equation. So we have ux is lambda sum I1 to n. So we have ci ui x. Okay, where c is a constant that we need to determine. If we can find what c is, then we can solve the given integral equation. So now we need to solve for c. Now, if you multiply this with v1x, v2x, and so on, vnx, and then we integrate from a to b to that equation. So what we have is that the integration a to b, integrate we multiply by v1 to that equation. So we have v1x ux dx. On the left side, on the right side, we have that ci summation of I1 to n ci, and then integrate a to b. So we multiply by v1, so we have v1x vi x dx. Okay, and then we do this for multiply by v2, multiply by vn, and so on. So what we have, we multiply this up to n, so integrate a to b vnx ux dx, that equal to lambda integrate summation I1 to n ci integrate a to b vnx vi x dx. Okay, now remember that we have this definition first, integration a to b vit ut dt as a ci. Okay, and also we define alpha, let's say ji, as integration of a to b vj x ui x dx. Okay, and then for, of course, for the j I1 to 1 to n, yeah, for I1 to n, as well as j. Then what we have, if we apply this into the first equation here, so what we can see, this is v1u, so we have alpha 1 alpha 1i, right? Alpha 1i u because that no, the right hand side here, sorry, right hand side here. So we have, so V1 Vi, no, should be no, the left hand side, sorry. So we got those things. So what we end up with the C1 is equal to, because this part is C, so we have if you look at the definition of C here, VITUT, so this is V1 X UX, so this is our C1, so that gives us C1. And then on the right hand side we have a lambda summation I1 to N, you have C I, and that give you alpha 1 I. Yeah. Or you can write this, rearrange that for the similar subscript, because this is summation of I to 1. So you can write this as a and then factor out C1. So we have 1 minus lambda alpha 1 1 C1 minus alpha lambda alpha 1 2 C2 and so on. Yeah, so we have lambda alpha 1n Cn that equal to 0. So if you proceed that with the second equation, third equation, and so on up to n equation, so what we find that for the second equation we have minus lambda alpha 2 1 C1 plus 1 minus lambda alpha 2 2 C2 and so on. Lambda alpha 2n Cn equal to 0, and you proceed this, you are going to have lambda alpha n1 C1 plus minus to be minus, in the end we have lambda alpha nn Cn equal to 0. So what we have now is that the unknown C1, C2, Cn, we can write the system of equation, system of linear equation as this form, equal to 0. Yeah, we have a homogeneous linear system equal to 0, where of course from here, yeah, from that is easy to see that if the determinant of A is different than 0, so what happened is that there exists a inverse of A such that A inverse, you got I, identity. So what happened that if the determinant is different than 0, so we have basically only a trivial solution. Yeah, so X here is a C1, C2, C3 up to Cn. So that's a trivial solution. So I can write as X as C1, C2, Cn, transpose of those. Okay. So in order to have the non-trivial solution, so we need the determinant of A is non-zero. Yeah, so we need to remember that if you want to find the non-homogeneous, non-trivial solution, so the determinant of those matrix is 0. So I can write those things. So the determinant of those matrix we can write as if you look at this matrix here. All right, you look at this matrix, the system of equation here. Okay, so of course you can write this in terms of matrix where the component, this is the component, that is the component, and so on and so forth. So the determinant of those things, yeah, that we have d, let's denote that as a d lambda is equal to, so we have 1 minus lambda alpha 1 1, we have lambda minus 1 2 and so on, minus lambda alpha 1 n, and here is minus alpha 2 1, here we have 1 minus lambda alpha 2 2 and so on, minus lambda alpha 2n, and here we have minus lambda alpha n1 minus lambda alpha n2, and so on. We have 1 minus lambda alpha n. So the determinant of our system. Now, having done those, okay, and then of course this in my notes I have some typing error there. Should be 2 1, here should be 2n. All right, and then the down here I have explained just now, if the determinant of this system has is different than 0, then it gives the trivial solution, which is C1 C2 equal to 0. So therefore, in order that to have the non-trivial solution, we need the determinant is different than 0. Okay. So if this is just the basic knowledge from the linear algebra. If the determinant is different is 0, then at least one of the C can be assigned arbitrarily, and the remaining Ci can be determined accordingly. Hence, when the determinant of our system is 0, then infinitely many solutions of the integral equation will exist. Yeah, and to find the eigenvalue, we want to find lambda. We just take the determinant equal to 0. Then we can find what lambda is. So the degree of equation that is lambda in lambda is less than m which is less than or equal to n. So therefore, if the integral equation 1, which is our homogeneous Freedom integral equation, has a separable kernel given by that I mentioned earlier, then the integral equation has at most n eigenvalues, and corresponding eigen function will be its solution. Okay, so that's the process of how to solve the homogeneous Freedom integral equation. Now let's see the example. Let's see the example. So let's say we want to solve the equation ux minus lambda integrate 0 to 2 pi sine x minus t ut dt that equal to 0. Okay, and the kernel, our kernel xt is given as sine x minus t. Of course, we can write this as a sine x cos t minus cos x sine t. So you can see that the homogeneous, the separable kernel can be written such way, yes, summation of function of x alone and function of t alone. So if you look at here, we have a multiplication of function of x and function of t, function of x and function of t. So which means in this equation our kernel is separable. Okay, so if we use that, expand that sine x minus t, so what we have to that equation, so we have ux is equal to minus lambda integrate 0 to 2 pi, so we have sine x cos t, I can put bracket here, minus cos x sine t, we need those bracket, that ut dt, that equal to 0. Okay, and then I can write this as a ux minus lambda. We can factor out those lambda. So what happened is that integrate 0 to 2 pi sine x cos t ut dt minus integrate 0 to 2 pi cos t sine t, cos x sine t ut dt, that equal to 0. Then I can let, and if you look at here, we integrate with respect to t, so which means the function of x we can factor out. So we have this uxt minus lambda. So here we have sine x integrate 0 to 2 pi cos t ut dt minus cos x integrate 0 to 2 pi sine t ut dt, that equal to 0. Yeah, this is 0. All right, now I can let that this part is as a, then I can let that this part equal to b. So what we have then, this is ux minus lambda a sine x minus b cos x, that equal to 0. Okay, so now we need to solve this equation. Yeah, we need to solve this equation. So how to solve that equation is that if we multiply this by cos and we integrate, we got one equation, and then do it one more, multiply with sine x and then integrate, then we got another equation. So if we multiply this by cos x and then integrate, so we have a ux cos x, then integrate 0 to 2 pi dx, then this one is minus lambda, we have a integrate sine x cos x dx, that you have plus lambda b integrate 0 to 2 pi, 0 to 2 pi, so we have cos squared x dx, that equal to 0. So for this you need to use the identity half 1 minus 1 plus, 1 plus cos 2x. So this is the odd function. We integrate over the one period, so that one period we call it. So this gives you 0, and this part here, if you integrate that will also give you 0. So what left is only 2 pi and 2 to cancel out. So what we have, and this part here, okay, so this part here, that one, is as we define A, so that gives you A. Okay, so we end up with A plus, we have lambda, we have B, and we have this is 2 pi and pi got here, because 2 pi cancel with 2, that we got 0. That's one equation. Then if you multiply that by sign, you can do the same process. You got another equation. Yeah, you got B minus lambda A pi that equal to 0. And then you need to solve this equation. Solve that. So what we have from there, solve for lambda. Yeah, the purpose we solve for lambda. So we will have, this is not difficult to solve that. You can do this thing. We have lambda is plus minus I over pi. Yeah, just substitute there. You have B equal to, yeah, from there we have B equal to lambda A pi, then substitute into 1 B, then you have those things. Now, so what happened in this case? So we have lambda is plus minus I over pi, because we have two cases here. If you substitute there, what happened is we can have you can factor out A. So we have 1 minus lambda squared pi squared, that equal to 0. So we have two cases here, either that equal to 0. If that equal to 0, that we have this, or A equal to 0. If A equal to 0, you have B equal to 0. Alright? If A equal to 0, you have B equal to 0. If AB equal to 0, and we substitute here A and B equal to 0, we have the trivial solution. Yeah, if it's this trivial solution, then we don't have the eigenvalue. That's true. So for, yeah, if lambda different than I over pi, so what we have basically is A equal to B, then that give you a trivial solution. Okay, for lambda is then for lambda plus minus equal to plus minus I over pi, we substitute into that, okay, and substitute into here as well, here lambda. So what we have is that B is equal to plus minus IA. Yeah, just substitute into here. Yeah, that. Okay, just put that lambda is 1 over pi, then you can have those things. So from there, if you substitute the value of B and lambda into the solution here, so basically we have ux. You can write this ux in terms of some constant cos x plus, or yeah, plus I sin x. That will give you basically this a plus minus, I think, plus minus, because we have plus minus here, so we should have plus minus. So this is basically a constant c e to the plus minus ix, where c is any constant. C is constant. Of course, our c constant here is in the form of alpha, in the form of the pi here. So In this example, for the kernel x sine x minus t, we have the two eigenvalue, which is lambda plus I over pi, then the other one is lambda minus 1 I over pi, and the corresponding eigenfunction is that u c e plus I x, corresponding to the lambda plus I pi, and then you have another one c e minus I x, corresponding to lambda negative I over pi. Okay, so that's the solution of our example. All right, so if you look at the notes, my notes here, I have I think you can well, you can have a look at this, but this is the I suppose remove this part here, but yeah, you can look if you want. But of course, this is not complete because many of the related notes for this part here is not included in this I mean in my notes, and also related to that. But there's some problem, some exercise that you can try using the separable kernel. Okay, this is obvious. You can separate that. This is also you can separate that, and then as well as others. So try this as an exercise. All right. So as a conclusion, so what I have done in this video, that I explain how to find the solution of the Fredholm integral equation, the homogeneous Fredholm integral equation of the second kind. Yeah, and then little bit notes, and as well as detail of the process, and as well as example. So I think with that I stop here for this video. Thank you. See you in the next video. Bye.